All right. Hi, everyone. My name is Sadi, and today I'll be talking about WebSockets and scalability challenges related to them. So let me start with an image that we had from an incident some time ago. Was a long Friday. We stayed until midnight, but eventually we fixed it. The alternative would have been to quit our jobs, move to another city. We didn't do that. We were able to fix it. We had a lot of learnings in this incident, but most importantly, it was a wake-up call that we need to improve the reliability and scalability of our system. So before I jump into more details, let me say a couple of words about myself. So I'm Sadi. I'm a software engineer and consultant at Netlight. Netlight is a tech consulting firm based in Europe. And I focus in cloud engineering, architecture, SRE, more recently also developer experience topics. And that's mainly my focus areas. So in this talk, I'll be laying out a little bit the context, so some basics about EV charging. Then I'll talk about WebSockets and the scalability challenges that I mentioned. And ultimately, I'll go into our approach, how we handle them, and maybe some of the things we discuss will be applicable in systems that you might be working on as well. So let's jump right in. Some context about EV charging. So let's first do a quick show of hands. So how many of you have driven an EV car? Yeah, nice. So a lot. So maybe you're already familiar with some of the frustrations that come with charging EV electrical cars. So let's take a look at how that flow looks like, so the charging process. So the EV driver would plug in their car at the charging station. And the charging station is connected to the electrical grid, of course, but it also has an internet connection via a mobile carrier. And it uses this internet connection to communicate to a system called the charging point operator. The communication happens over WebSockets and with a protocol called OCPP. It's just an open standard, and it makes possible to operate stations from different vendors, and it determines what the flows should look like, what the messages look like, and so on. So nothing special about that. The charging point operator, on the other hand, is a system that companies that are interested in offering charging solutions would build. Right? And that's what we built in one of our largest EV charging clients, where I've been for the last 2-3 years. I've been leading the platform team, and in this team, basically, the goal is to build easy-to-use, reliable interface for charging stations, to communicate to charging stations. We take care of stuff like station management, charging station handling, authorization, remote start and stop, if you want to control your charging experience via a phone, for example, firmware updates, load management, and a lot of stuff of that nature. This is what our baseline architecture looks like. So on the left-hand side here, we have services in the platform service that we call them. And the WebSocket gateway component is the entry point for charging stations to connect to our system. It's quite limited in scope. It does some parsing, some rate limiting, and it maintains. The main responsibility is to maintain this WebSocket connection. Then we have the station management service, which implements most of the OCPP logic, most of the core business logic in our system, charging session handling, session authorization, and so on. While later on, we have services which are smaller in scope, like the firmware service, history service for analytics and for some time series data, diagnostics, config service, and all of this is exposed to our product teams via an API, so asynchronous and asynchronous APIs, to build products like fleet charging, home charging for users who are buying a charging station and installing it in their homes, or dealer charging for companies that want to offer charging at their facilities, and a bunch of other products that this client builds, so be it B2B or B2C. So let me do a quick primer about WebSockets. So even if you haven't heard about WebSockets before, you can still follow the talk and learn about the challenges and our approach to them. So basically what WebSockets is, it's a protocol that enables bidirectional communication between a client and a server. It gives you a full duplex communication channel over a single TCP connection. And the benefit over HTTP is that you can avoid all this overhead of reestablishing the TCP connection every time you want to send a message. So that's great. That means you can get rid of that overhead. But of course, the cost is that now the server needs to keep track of the state, right? So it needs to keep track of this connection, and that makes it stateful. These connections are long-lived, and that brings us to the challenges or to the trouble with scaling out WebSockets. Or maybe a little bit more about WebSockets. So some applications are real-time communication applications, chat-based application, stock tickers, multiplayer games, stuff of that nature. And it's also what the stations use to communicate to the server. So the trouble with scaling WebSockets, let's go to the first point. So one part of the problem is related to load balancing. So consider the situation on the left. So we have a network load balancer. It uses standard round-robin strategy. And let's say we have 4 replicas, so 4 pods of this WebSocket gateway component. And each of them have 8,000 stations connected to them. So they are maintaining 8,000 connections. So this would be an equilibrium state, right? So the connections are nicely distributed. It's an equilibrium state. But if there is a restart for whatever reason in one of the pods, the situation changes easily, and so the load balancer would redistribute those connections. The stations, after they get disconnected, they would try to reconnect. Those connections would get redistributed, and it might look something like this. So we have the first 3 pods now maintaining 10,000 connections, and the last one 2,000 connections. So easily a restart or a pod rescheduling or whatever might cause a pod to restart might cause the system to enter in a state which is out of equilibrium. So this is not a big deal, right? Because eventually, due to station reconnections, this will again stabilize at some point. It will go to an equilibrium, but that might take an indefinite amount of time, right? So because the stations, they usually don't reconnect that frequently. If there isn't some cause that causes the disconnection, right? So that's one issue. Another issue is something that I'd like to call reconnection storms. So I mentioned earlier that the stations are using this mobile carrier to connect to the internet and to our system. So let's say that we have carrier 1, carrier 2, and we have a group of stations that are connected via carrier 1, and another group by another carrier, right? So they go through our load balancer and to this WebSocket gateway component. Now, if there is some outage in carrier 1, like a regional outage or whatever might cause some downtime in this carrier, that means that these stations will lose their connection, and at the point in time that the problem is resolved, they would try to reconnect all at once, so at the same time. And what this does is basically it causes unpredictable load spikes. It's a little bit like an accidental denial of service attack with all of these stations coming back all at once. And the typical, or what helps here usually, or the typical approach is to introduce some sort of retry with exponential backoff. The problem we have here is that we don't have any control over the client behavior, the retry behavior, because it's the vendors, the station vendors that implement the firmware, and they decide what the retry looks like. In theory, they should implement retry with exponential backoff, but in practice, we see that often it's not the case, and the station simply retries as soon as it disconnects, it retries to connect. And that's what leads to this behavior. There might be different triggers. So one trigger that I just described is the network carrier outages, but there are also more benign things like a WebSocket gateway release, right? That also causes the stations to reconnect, or a pod rescheduling, right? If that pod maintains a lot of connections, all of those connections suddenly drop, and the stations try to reconnect at once. So some implications that this sort of behavior, this reconnection behavior has, is that it puts our system always in a risk of positive feedback loops, right? So let's say a large amount of stations reconnect all at once, and now that might cause some pods to crash. For example, they run out of memory. And now those pods that crash, the stations that were connected to those pods, they would lose their connection. And that causes now a bunch of other reconnections to happen again, right? And this might lead to this positive feedback loop and potentially cause the system to enter a state that it cannot recover from automatically or by itself. Another problem is related to load spike propagation. So even in the case that the platform is able to take in the load or to take in these reconnections, we have a bunch of downstream services which might be just interested in part of what's happening in the platform. And suddenly, if a huge amount of traffic comes in from the platform and we propagate this traffic to the downstream services, that might be a problem for them and their databases and their bottlenecks. And another less serious problem is, so when a station is disconnected, the user experience with that station is kind of bad. It's not completely unusable. You can still charge in most stations depending on the configuration, but it's not a good experience from the users. So for example, all the remote control features are not usable. Maybe authorization doesn't work depending on the configuration. So it's definitely not a good experience with that station for the user. And since we know that the release causes some downtime in this station connection, we introduced a maintenance window rule. So, which is not a big deal in itself, but it's pretty annoying, and it goes against our continuous delivery practices. We have to always announce it, and it's quite annoying. So that's also one thing that comes with this. So yeah, I've discussed the implications. I discussed a little bit the challenges with this. Back to our incident that I mentioned at the beginning. This was also triggered by a spike in reconnections. So it was a combination of factors. It wasn't like a single thing, but was the size of the database, instance, the pod limits for memory and CPU, and it was a combination of things that led to this state of instability that it couldn't recover from. The root cause was something else. It was a misconfiguration in the logger. It was batching a lot of items in memory, and that caused some back pressure, which eventually caused the pods to crash, right? And because of this reconnection behavior, this turned into a positive feedback loop, and the system could not recover by itself. And worth noting that the logger had been like that, had been configured like that for a long time. It's not that we changed this in a release, but it simply entered this because you see this little bump in the beginning. It simply entered this state because of a reconnection. So that was the trigger. It was quite hard to distinguish between cause and effect here during investigation. But this reconnection flow was something that we identified that we needed to fix and make it more reliable, so make it give us more confidence that our system can handle a large load of reconnects and can handle the traffic that comes from the stations. I really like this quote from Google's SRE book. Reliability is very important, and it's certainly true in our case. So our core business or our core value proposition to the product teams is basically reliability. So we knew that we had to do something, and we needed to improve the reliability and scalability of our platform. So with that, let me go into the section about how we address the challenges and how we evolved our system architecture to do this. So let's first take another look to the connection flow. So I listed the steps here, but I won't go through them. It's mostly for completeness. So it's pretty straightforward. We have the station here. We have a network load balancer, is a pass-through load balancer in GCP. And we have WebSocket gateway and station management service that I mentioned earlier. Both of them are horizontally scaled. So in WebSocket gateway, we do the TLS termination. We do some parsing, some rate limiting. And then in station management service, we save a bunch of stuff, a bunch of details about the connection in the Postgres database. And we do a couple reads, a couple writes, and that's basically the connection flow. And during times of high load, what happens is basically the database can become a bottleneck. And this causes the problems that I mentioned with the reconnection flow. It causes high latencies in the connection, and that can spiral into feedback loops. So some quick remedies. Oh, yes. Some quick remedies is basically throwing money at the problem, right? So we just use another larger database instance, and that works great as a temporary solution, but it's wasteful. Yeah, it's costly as well. So, but it works great. You know, if you just, especially during incident handling, you just want something to make the fire go away. So it's great as a temporary solution. Another more subtle solution or thing that you can do about this is related to the HPA behavior. So there is this thing called the stabilization window. And the idea here is that we want to reduce as much as possible the reaction of the HPA to fluctuations. So because a reconnection, we want to reduce as much as possible reconnections that we cause, right, from our side, because that makes the experience at the station worse. So we want the station to stay connected as long as possible. If it disconnects on its own, that's okay, but we want to reduce the disconnections that we cause from our side. So this fluctuation window, this stabilization window reduces the fluctuations caused in the replica size from the HPA. And a good way to find a value here is basically to experiment and see what works for your load parameters, for your traffic that you're serving, and so on. But we needed also more long-term solutions, and some goals that we set is basically we want to make the connection flow more lightweight, want to make it more easy to scale, and that would help us alleviate the database-related bottlenecks. Another goal is to decouple downstream services, right? So to put a stop to this propagation of load, right? So to make it possible that the downstream services can be scaled independently of the scale that we need for the platform. And also we wanted to reduce the disruptions during the releases. So let's start with that first point, so optimizing the WebSocket connection flow. Okay, this is not new, the connection flow again. So we are saving a bunch of fields in the database during the connection flow, right? So when the authorization happens, we are saving things like the last seen, last connect, the WebSocket gateway pod IP, some certificate details for stations that connect via MTLS. And as I mentioned, the database is a potential bottleneck here, right? The key observation is that this data that we are storing in Postgres, we don't really need the durability guarantees that Postgres provides, right? The data is ephemeral in nature. It's just connected to the current connection that we have, and it can be easily recreated if we were to lose that data. So we don't really need the durability guarantees from Postgres. So what we changed here is basically introduce this connection service, which uses a Redis database. And it's a great fit for this ephemeral, for this data, which is ephemeral in nature. If something were to happen to the database server, we can easily recreate that data by having all the stations reconnect. That's without going into the Redis backup mechanisms and so on. So, and it boils down to basically memory being faster than disk, and it's a better fit for the station connectivity flow. And some outcomes, so what we observed is that we were able to reduce the connection establishing time by 1 order of magnitude by switching to this flow. We reduced the load on the Postgres database significantly. Now, it doesn't, we don't have to reach out to the database during a station connection flow. And we were able to scale to a much more reasonable size because this database doesn't really need to be large enough to take the peak of the traffic or the peak of the load that the total amount of stations can cause, right? It no longer needs to be able to do that, so we can scale back to a much more reasonable instance size. And also we took this chance to make the connection flow a bit more maintainable. So it was intertwined previously with a few other flows, like the station certificate renewal flow, for example. And since we were restructuring a few things, we took this opportunity to also refactor and make it a bit more maintainable. Yeah, so that's the revised flow here. However, we still had this problem with releases, right? So we still had this problem that releases would cause disruptions, and that's something that was under our control, right? And ideally, we want to be able to release as often as possible, even though this is a smaller component that it's isolated in scope, and it's not that we need to release that often, but often when we're building something new or changing, improving some, or doing some optimization, you want to be able to iterate quickly. So the root of the problem is basically with the rolling updates that we were using. So let's do a quick recap of what rolling updates are. The idea is to incrementally replace old pods with new pods, right? And there is the max search and the max unavailable parameters, which let you control how fast this happens. So in our case, it would go a little bit like this. To take this simple example, we have one station, we have 3 replicas there in version 1, and we want to go to version 2. So when we start the rolling update with these parameters, we would firstly scale down a pod from version 1, and then bring up a version 2 pod. The station would reconnect back, and we would have to repeat this a couple of times, right? Until all of the pods are in version 2. And even in this simple example, you see the station reconnected 3 times with just 3 pods, right? You can imagine what happens with more stations, with more pods, and all of these excess reconnections that also cause additional load, by the way, would ideally be avoided. And this is a lot of disruption that a release is causing. So basically the takeaway here is that rolling updates are not a good fit for deployments sensitive to disruptions. In our case, that's our WebSocket-based application is basically sensitive to these disruptions. So ideally, we'd want to avoid that. But in a bunch of other places, rolling updates are great, right? They come out of the box. They give you 0 downtime deployments. That's a perfect fit for most applications. But in this case, where it's sensitive to these disruptions, ideally, we want to avoid this. So our solution is basically to switch to blue-green deployments. A quick recap. So the idea is, so let's say we have, again, 3 replicas here. We would bring up version 2 replicas, and then once they're ready, we can run some checks, look at some metrics, and once we are confident that it's ready to serve traffic, then we can switch traffic all at once. And ideally, the stations would only reconnect once during this process, right? So they would lose the connection when the load balancer is switched, and then immediately connect to version 2 instances only, right? And this reduces the disruptions quite significantly. Then we can also run some post-promotion checks, of course, to verify that everything is right. In our case, we used Argo rollouts. It's pretty cool. It has a lot more features than we used, and we were very happy with it, so I definitely recommend to take a look if you're interested in trying out blue-green deployments. The chart on the left also shows a little bit what I was describing. So we have connections, the number of connections on the y-axis, and time on the x-axis. And with rolling updates, this is what happens. So, of course, we have a drop, and then it takes a while to recover back to the normal amount of connections that we had. But with this is the time window. With blue-green updates, or with blue-green deployments, this is much faster. The time that it takes to recover back to the normal state, or to the state where all stations are connected, is a lot shorter. And by some measurements that we did, we saw that it's around 80% on average. So it's a pretty good deal, I'd say. The return of investment is pretty large, considering that we were able to do this by simply switching to blue-green deployments. Effort-wise, that's pretty little. Good. Then let's jump into the circuit breaking aspect using event queues. So here we wanted to target basically this load propagation nature in the system that happens when stations reconnect. And the approach that we went with is going towards event-driven architecture. So people mean different things with event-different architecture. It means different things to different people. But I think a definition that a lot of people would agree is that it's an approach to build services that communicate with each other asynchronously via events. An event is both a fact and a trigger, which is expressed as a notification. And what it looks like, typically you'd have a producer, and when something happens in the domain of that producer related to some business flow, for example, station connected or station disconnected, charging session started, and so on, they would put this event in the event queue, in some queue of sorts, and then a consumer would decide, based on that event, to either trigger some logic of its own or simply ignore it. So it'll take, I put a couple of links about event-driven architecture in the slide. It'll take a talk of its own to really do it justice, but I just wanted to set some context here. And in our case, the reasoning goes a little bit like this. So event-driven architecture really helps us do circuit breaking between the platform and downstream services. We are using GCP PubSub, which is pretty good. It's a managed service. We use push subscription, and they have something called some mechanism which is similar to TCP congestion control. So it avoids overloading the subscriber service in times of high load or when the subscriber is knacking a lot of messages. So it backs off and it tries to automatically detect when the subscriber is in some trouble, and then when it's again hacking messages like normal, it scales back the sending of messages. So it's quite similar to TCP's congestion control algorithm. And also, if you're using pull subscriptions, there is flow control. You can determine that on your own, so you have quite a lot of control. It helps decoupling services and teams. This is something that we also was one of our goals, and it's definitely by no means the only way to do this, but in our experience, it's something that really helped us to determine the boundaries between the domains, between the teams better, and stuff like event storming, for example, helps a lot in determining these boundaries. And it's definitely event-driven architecture helps with this decoupling, even though it's definitely not the only way to do this, or it's not a necessity either. And also, our business flows are really asynchronous in nature. So it's really, it can be modeled well by event-driven architecture and by asynchronous communication, because the underlying business processes have that nature as well. But of course, one has to be mindful of the trade-offs and make a deliberate decision here. So one trade-off, for example, is eventual consistency, right? So definitely, we try to apply event-driven only when it makes sense in that context, and it represents well the underlying business model. So event-driven is pretty cool, gets you a lot of street cred. It's right up there with rewriting your system in Rust. But that doesn't mean that one has to apply it mindlessly everywhere. So we try to be careful about the trade-offs and really be deliberate about our decision-making in design there. Yeah, the takeaway maybe from this slide is that to be successful with event-driven architecture, I think something which is very important is to lower the barrier for the teams to event-driven architecture. So in terms of building good abstractions, in terms of the conceptual topics that needs to be made clear when switching to event-driven, especially if the teams are used to building stuff in a synchronous way, if they are coming from that. And we found that a lot of things help here. So knowledge sharing sessions, being very disciplined in the event schemas and documenting them, and making sure that you're not introducing breaking changes between the versions, or having a proper versioning strategy, guidelines, being disciplined about dead letter queues and a strategy how to handle them, message trying. So having the right abstractions and having the right tool set really makes a difference here in successfully adapting event-driven architecture. And that's about it. So to summarize, there is no panacea in tackling the challenges with scalability in WebSockets. So in our case, we made the WebSocket connection flow more lightweight by introducing an in-memory database for the ephemeral data that enabled us to remove a little bit the load from the Postgres database and, in general, make the connection more lightweight, easier to scale, also scale it independently from the Postgres database. We were able to reduce the disruptions during deployments by switching to blue-green deployments. So we discussed a little bit how the deployment strategy can have an impact on the reliability of your system during these deployments, and how blue-green deployments might be a better fit for WebSocket-based connection, for WebSocket-based applications, or in general, maybe even applications which are sensitive to connection disruptions. And finally, we talked about circuit breaking to stop the load spike propagation and the usage of event queues there. So yeah, in general, an analysis of the load patterns, an analysis of the bottlenecks in your system is crucial to inform decision-making about your system design. And with that, I'd like to go into a questions and answers session, and that's been it. I hope you enjoyed it.